Hello, my name is Magnus Petersen. This video is about backtesting and optimizing a stock screener, and it is made as part of tutorial number 7 for the SimFin project, which is a financial database with a beautiful Python API that makes it very easy to download and work with the data. You can download this and install it on your own computer by following the link below the video, or you can run it entirely for free in the cloud without installing anything on your own computer. And the instructions are also in the link below the video. So this is implemented in a Python notebook, and we have to import two things from SimFin. First, we import the SimFin library itself, and then we import all of the names for the data columns, which makes it a lot easier to address them when working with the data. Then we have to configure the SimFin library. First, we have to set the directory where the data is saved when it is downloaded from the SimFin server. It is saved to disk so that the next time you want to load it, if the data is still considered fresh, then it is loaded very quickly from disk instead of having to download it from the server again. Then we set the API key for SimFin, and this is also loaded from disk, and if the file does not exist, then it uses the default key, which is just free. The data is basically the same, but for the free dataset, it is delayed 1 year. So if you want to get data up until today, then you have to buy a subscription to SimFin, which is very cheap. So the easiest way to load and process data using the SimFin library is to create what is called a stock hub or a data hub, and we specify which market we're interested in here. It is for United States. At this point, there's only a little data for Germany and a little data for various other countries. Mainly, it's a database for United States at this point in time. But once again, that's why it's important for you to support the project if you want to see data for more countries. Then we specify how often we should refresh the data, and this is only for the fundamental data. And here we specify how often we want to refresh the share prices. At this point, the data hub has not loaded any data at all. It has just been prepared. So the tutorial explains how you make a basic stock screener using SimFin. And I won't go through all of that now. I think I did that in the previous tutorial I made on SimFin. What we're going to do is we're going to scroll down until we get to the backtesting, which is here. So first we have to calculate all of the signals, and the data hub can do that for us using just very simple function calls. So fin signals, that is like return on equity, return on assets, net profit margin, things like that. Growth signals are like sales growth, net income growth. Valuation signals are like price to earnings ratios, price to sales ratios, market cap, and so on. These functions will automatically download data from the SimFin server, load them into pandas data frames, compute the signals, save those to a cache file on disk because it takes several minutes, so that the next time the functions are called, it can load the cache files instead of calculating them all again, and then it returns a pandas data frame. Then we combine all of those data frames into a single pandas data frame. Then we remove the outliers. Then we calculate 1 to 3 year average stock returns, and these are actually the log stock returns because that is easier to implement using vectorized pandas and numpy functions. But for these value ranges, the mean log returns are very close to the ordinary mean returns. Then finally, we combine all of the signals and the mean log returns into a single data frame. And when this is run, it prints the status of what it is doing. So it downloads datasets, extracts a zip file, loads it from disk into a pandas data frame, and so on. Then it says it cannot find the cache file for the financial signals, so it runs the function that generates those. Then it saves the cache file to disk, and it does the same for the other functions. Altogether, this takes about 7 minutes to run. But because of these cache files, the next time you run this, it only takes some seconds. Unless it has refreshed the files with financial data from the SimFin server, then it has to recalculate all of these functions again. But all of this is handled automatically by the data hub, so you don't have to think about it. It just refreshes the data from the server whenever it gets too old, and then it also refreshes the cache files. So now we can actually create a stock screener very easily. We do this by making a Boolean mask. So we take the data frame for the signals and the stock returns, And in this screener here, let's say we are only interested in stocks with a market cap above $1 billion. So what this creates is a Boolean mask that we can use to look up those matching rows in the pandas data frame. We can then add criteria to this stock screener simply by adding more Boolean masks together. So for example, we can say that the current ratio must be greater than 2, the debt ratio must be less than 0.5, the price to earnings ratio must be greater than 0 and less than 20, and so on. And finally, we use this Boolean mask to take only the rows where all of these stock screener criteria are met. So let's look at the average 1 to 3 year stock returns when using the screener and not using the screener. So first we have a column here in this table that shows the basic statistics for when we're using the screener that we just made. Because there are some outliers in the data, the mean stock return is maybe not so useful. So let's look at the median instead. If we use the stock screener above, we get about 14.6%. And if we did not use the stock screener, if we just take all of the stocks in the database, then the return would only be 9.1%. I know it is a little confusing because this is the median of the average log return. But roughly what this means is that if you had used this screener and you had made a diversified portfolio with all of those stocks that the screener gave you, then it would have resulted in a return of something like 14.6%. Whereas if you just had taken all of the stocks in the database, it would have been about 9.1% per year. We can also make a scatter plot where on the x-axis we show the price to earnings ratio, and on the y-axis we show the average 1 to 3 year stock returns. And again, these are the log returns, but they are approximately the same as the normal returns. The hue of the dots is the return on equity, but overall what we see in this plot is basically just a blob or a mess of random points. This means that there's no direct connection between the price to earnings ratio and the future 1 to 3 year stock returns. We cannot say that in general for all the stocks. And also I should mention that when we calculated all of the signals for price to earnings ratio, sales growth, and so on, we actually took the 3 year averages. So in order to calculate this PE ratio, we would first take the average of the last 3 years' earnings and then the daily share price and use those two numbers to calculate the PE ratio. And this is done to smoothen out the year-to-year variance in the earnings and sales growth and so on. So now let's make a scatter plot where we only show the data points that matched our stock screener. And I should also mention that these plots are only a random subsample of all of the data points, because if we show all of them, it would just be a complete mess. So we take a sample of 5,000 points, and it gives us a fairly good idea of what the distribution looks like. So the result here when we have used the stock screener is not quite as random as the plot we just saw before where we had not used the stock screener. It is still a bit messy, but there is actually an interesting tendency which will become even clearer in a moment. But anyway, the distribution does appear to be slightly shifted upwards and concentrated in this region here, which has a stock return between 0% and 25%. And that appears to be where the bulk of all of the data points are located. So now let's try and make the same plot, but for a small random selection of stock tickers. So here we can see that this here is for one stock, this is for another stock, the blue here is for one stock, the pink or whatever is for another stock, the green here is for a stock, and so on. What you can see is that there's a tendency to have a particular kind of downward sloping curve. And if you run this notebook again, you get another selection of 20 or so random tickers, and the plot will be different, but you can see that the slopes of the curves look kind of the same. They are just shifted up or down in the plot. And this is one of the things that I have been investigating in my other finance research, is that why do we actually observe this particular behavior in the plots? And there is a very good mathematical reason for it. And it has to do with the fact that when you're doing long-term investing, there are only really 3 things that matter. The first is the dividend. The second is the growth in the per share numbers, for example, the sales per share. And the third is the revaluation. So for example, the change in the price to sales ratio. But you will have to watch my other videos for a detailed explanation of that. But it is actually a quite remarkable discovery, and to my knowledge, it is completely original. I haven't seen it in any finance textbooks anywhere or finance research papers or whatever. But anyway, now that we have showed how to do backtesting of a stock screener, you can use that backtesting to manually modify the criteria for your stock screener and go over that again and again and again to gradually refine the stock screener. We can also do this automatically by using an optimizer. And because we cannot make this as a simple mathematical formula, we need to use a so-called heuristic or black box optimizer. And there is a fairly good one in SciPy, which is called differential evolution. So let me show you how that works. First, we have to define the boundaries for all of the parameters, and we will make a simplified stock screener. So we want to have a minimum for the market cap, we want to have a maximum for the debt ratio, a minimum for the price to earnings ratio, a maximum for the PE ratio, and so on. And these are the boundaries for the parameters that we allow. So for example, the market cap must be somewhere between $1 million and $1 trillion. The debt ratio must be between 0 and 1, and so on. Then we make a function for performing the stock screener. It takes the input x, which is just an array or a list of parameters for all of the criteria for the stock screener. So we unpack this array here to the minimum market cap, the maximum debt ratio, the minimum PE ratio, the maximum PE ratio, and so on. Then we run the stock screener just as we did above. That is, we basically create a Boolean mask, and then we use this Boolean mask to look up the matching rows from our dataset. And then we return those rows. Then we define what is known as an objective function. It is also called a cost function or a fitness function. And the optimizer that we are using does minimization. So what this must return is a floating point number that must be minimized. So once again, it takes as input an array x, which contains the parameters for the stock screener criteria. Then we run the stock screener using these parameters, and we get the matching rows from the dataset as I just described. And it is perfectly possible that the stock screener couldn't find any stocks at all because of the criteria parameters being set in such a way. But in the case that it actually did find any matching rows, we start by getting the 1 to 3 year average stock returns. Then we remove the outliers, and I just see here that this is actually really stupid to have inside of this function. So before I upload this to GitHub, I will take this out of the function so it doesn't have to be run every single time that we run this function, which will be run thousands of times, and this is actually a fairly expensive function to run. So let us just assume that we have already removed all of the outliers somewhere else. So now we just have the future 1 to 3 year average returns for all of the stocks that we're matching. Then we calculate the average of those. And because we are actually interested in maximizing the average stock return, but the optimizer will want to minimize the objective that we are returning from this function here. So we just negate the average stock return here so that it becomes a minimization problem instead of a maximization problem. Now we will penalize the objective in order to try and push the results in the direction that we want. And we do this by making a penalty factor, which we initialize to 1, and then we will gradually lower this towards 0 whenever we find out that our result contains something that we do not like. And finally, we will multiply this penalty factor with the objective so as to make the overall result worse when there is something we want to penalize. For example, we don't like few data points, because we can't really rely on the results. We don't know if it's going to generalize to other stocks in the future and whatever. So we make a limit of, say, 50,000 data points. So if there are fewer data rows that are matching our stock screener, then it will start to penalize the objective. Similarly, if there are less than 100 unique stock tickers that have been found through this stock screener, then we will start to penalize that as well, because we want the stock screener to work for a diverse set of stocks. Then we also penalize if there are fewer than 50 stocks per day on average. And then we want to penalize if the PE signal is missing because it is so important for our screener. And then we simply update the objective with the penalty factor. In case that the stock screener couldn't find any matching rows at all, we just return a really bad objective and says, don't use this stock screener parameters. And then we can run the optimization just by this function call here. And this takes several minutes on our quad-core CPU, and it prints status during the optimization like so that gradually it finds better and better parameters for our stock screener criteria. And then we can see the optimal parameters that it has found. The market cap must be greater than $40 billion. The debt ratio must be less than 0.64. The price to earnings ratio must be greater than 10.8, and it must be less than 49.5. The return on assets must be greater than 0. The return on equity must be greater than 2%. And again, these signals are calculated for 3-year averages. So the 3-year average return on equity must be greater than 2%. And here we have the sales growth must be greater than minus 18% per year on average for the last 3 years. We can then run the stock screener with these optimal parameters on all of the historical data in our database, and we can plot the results here. So on the x-axis, we again have the price to earnings ratio, and on the y-axis, we have the 1 to 3 year average stock returns. And we can see that these are mostly limited between minus 20% and plus 40. And it appears that the bulk of the points are somewhere between 0% and 20%. And we can also print some statistics. This shows us that we have almost 100,000 data points. The average stock return was about 10.5% per year. The median was about 12.1%. And you may remember that this is actually below the about 14% median that we had for the stock screener that we had made manually above. So it might look like that this is actually worse. The reason is probably that we had all of these penalties on the objective function for the optimization. And I have actually played around with this a little, and you should be able to get it up to something like 15-16%. This plot shows how many stocks were invested on each day. So it starts out around 30 stocks per day, and it ends at around 80 stocks per day. But remember that we penalized the objective function if it had less than 50 stocks per day on average. So it has tried to find stock screener parameters that would result in the average number of stocks per day being above 50. And that seems to have worked out. So this plot shows for each day the average stock returns going forward for the stocks found by the screener with the optimized parameters. And we can see that it works better for some periods than other. For example, here it gets between 15 and 20% per year. And down here it only gets around 5% per year if we had made a diversified portfolio of all the stocks found by the screener with these optimized parameters. But still, it's actually pretty good. And now the stockbrokers in the United States don't charge a trading commission anymore. It's basically free to trade stocks in the United States now. So you can actually make a screener like this and do this kind of investing yourself, sort of to make your own little investment fund, invested in like 50, 60 stocks. The commissions are not gonna kill you anymore. So even just the basic idea seemed to work really well. And I have written down a few more research ideas that you can try. First of all, you ought to split the dataset into training and test sets. And we show how to do this in some of the other SimFin tutorials on machine learning, because you want to know if the screener parameters that you found for some stocks, will they also work for other stocks? You want to avoid so-called overfitting. The next idea is that you can try and create a so-called ensemble of stock screeners by making different screeners that are specialized for different things. For example, one stock screener could be specialized for high growth companies, another screener could be specialized for undervalued companies, yet another stock screener could be specialized for small cap stocks, another one for mid cap, and another one for large cap stocks, and so on. You can also run the optimization many times, for example 10 times for each of those stock screeners, and then you can take the average of all of the outputs to create your final investment portfolio. And that might help alleviate the problem we saw in the plot above, where if you just have one stock screener, it works better for some periods than others. Maybe you can make an ensemble of stock screeners so that you get a more average performance for all of the years. You can also use a multi-objective optimizer to find trade-offs, for example, between average returns and the probability of loss. And I have made another kind of research paper or tutorial with a YouTube video on how to do that. And there's a link here that you can click. Bong, there. The most advanced idea I have written here is to use so-called genetic programming to optimize both the screener parameters and the entire screener formula. So which signals are you interested in? Should they be ANDed together or should they be ORed together? And what would the optimal parameters be for that screener formula? And if you try any of these ideas, then I would strongly encourage you to put it on GitHub so others can see the results and learn from them. That is what SimFin is made for very easily creating and sharing financial research. Good luck!